and my research specialty is OCT and targeted fluorescence and Doppler and polarization. And I have a group. We have a group of about 4 staff members that are involved in various the development of various instruments for biophotonics. And what I want to talk about today is Raman spectroscopy, Raman scattering, and coherent anti-Stokes Raman scattering. And the staff member in my group that is most involved in this research is Freka Ries, and you might have had him as a teacher already. Okay, so Raman scattering is a very special process. It's very inefficient, unfortunately, but it gives very detailed information, and I want to explain to you today how this works. So the normal scattering process involves a photon, an electromagnetic wave, that interacts with the electron cloud around a molecule, and because it's an electrical field, it exerts a force on this electron cloud and actually puts them into motion. So this electron cloud starts to move, shake around its equilibrium position. And we all know that a moving charge creates another electric field. And so an incident photon or incident electromagnetic field makes an electron cloud around a molecule shake. That in turn creates an electromagnetic field, which is emitted by the molecule, and that is the process of scattering. And this is called elastic scattering because there is no energy transfer from the incident photon to the molecule, and so the emitted wave by the molecule is of the same wavelength or same frequency as the incident wave. But it has changed direction, so there is a transfer of impulse to the molecule. So this is the elastic scattering process. But in 1923 to 1925, theoretical physicists like Smeckel, Kramer, and Heisenberg postulated that in the scattering process, the photon could also transfer energy to the molecule, and that would be then an inelastic process. And this would involve the change in one of the molecule's quantum states. So when there's energy transferred to the molecule, that energy should go somewhere. And as you will see, it turns out that this energy transfer to the molecule is a vibration. So there is what you create is an internal vibration of the molecule. And you can imagine having a molecule with 2 nuclei, hydrogen, H2, for instance. So you have these, I don't know if you can see my screen, but you have 2 molecules and they can vibrate with respect to one another. Sorry, 2 atoms, and they can vibrate with respect to one another. So you can have an equilibrium state, they're stationary, and you can excite them and they start to move with respect to one another. So that's a process of energy transfer to the molecule. So in the 1920s, so that's about actually a century ago, the Indian physicist Raman attended a conference in Europe, and he was fascinated by the blue hue of the Mediterranean, the ocean, and by glaciers, and that got him interested in the scattering process of light and how this occurs. And so back in India, he established a research group to study this scattering phenomena, and this is Sir Raman. And he won actually the Nobel Prize in 1930 for his work on the scattering of light and for the discovery of the effect named after him, which, you know, the Raman scattering effect. And it's an amazing feat. You have to realize in the 1920s, no lasers existed. If you wanted a powerful light source, the sun was one of your best options, or mercury lamps. But these light sources have a completely different power from a laser. A laser is a very coherent, directed beam, which can easily create tens of watts of power. And you can't compare that to sunlight, which is basically incoherent and doesn't have that very nice coherent properties of laser light. So it's a remarkable feat that Raman was able to discover this Raman effect just using the resources of his time. And this is the title of the paper that earned him the Nobel Prize, a new type of secondary radiation. It was published in Nature in 1928. And as I've just shown you, in 1930, he already got the Nobel Prize. And that is an example of how important that discovery was regarded at that time. I mean, within 2 years of the discovery of this scattering effect, he received the Nobel Prize. If you look, for instance, at the Nobel Prize for the discovery of the Higgs boson, that was predicted in the 1960s. And it was discovered, I think, around 3 to 5 years ago. So that took around 55 years for Higgs to receive the Nobel Prize for his discovery. And so Raman was a speedy guy. So like I explained, the process is a transfer of energy from the photon or the electromagnetic wave to the molecule. And what you can see here is the laser light. Can you see my red pencil on the screen? Is that visible?
Yeah, we can.
Yes, we can see it.
Does it update fast, or is there a significant lag? I'm now circling lambda 1.
There's a little delay, but
okay, so I'll try to annotate first and talk later. So we have a wavelength 1 that is incident on that molecule that in this case consists of 2 atoms. And what happens after the photon or electromagnetic wave has hit the molecule, afterwards the molecule starts to vibrate. So these nuclei start to move in and out. And at the same time, a wavelength of a different wavelength is emitted by that molecule. And because there's energy transfer to the molecule gets into a higher energy state. The wavelength that is emitted is of a longer wavelength, of a lower energy. So we get a shift from a shorter wavelength to a longer wavelength. And just to give you an idea of how you can study this, for instance, you take a gas and you use a mercury arc line to illuminate that gas. And the light that's emitted by the gas, you make it fall on a grating that separates it into different directions. Then you use a lens to focus it, in this case on a photographic plate. And so what you see in this graph here is the spectrum that is recorded by the photographic plate. And the first thing that we see is this very strong central wavelength. It's called the Rayleigh band. I don't know if Dirk has used the word already, the word Rayleigh scattering for the elastic scattering process. So these are the photons that have the same energy as the incident photon. And so this peak, this very strong peak, is the elastically scattered light. But if you look closely at the surrounding of this central peak, we see wavelength. Oh, Dirk just confirmed that he discussed Rayleigh scattering. That's great. We see other peaks, and I'm making these arrows red now, these 3 arrows, and these are peaks at a longer wavelength. And we see here a shift of the incident light to wavelengths of a longer frequency. And then also here a 4th wavelength. That's actually 2 tiny little bands. So what we see, we observe when we shine light on this gas, is not only the elastically scattered light, the Rayleigh scattered light, but also light of a longer wavelength, lower frequency, lower energy. And so these are now these famous shifts that occur when the molecule starts to vibrate internally. There's another thing that we can observe, and maybe surprising, but if you look at this part here, we see also waves with a shorter wavelength than the incident light. And so this is these are now photons that have a higher energy that is emitted by these gas molecules. And has any one of you an idea of how we can create photons with a higher energy in the scattering process? What should happen for these photons to pick up energy?
I guess that the instant molecule is already in a higher excited state, so it could be multi-photon absorption.
You're very right that this is the process where the molecule is already in a vibrational state, and what can happen then in the scattering process is that that vibrational energy of the molecule is now transferred to the photon, and so the photon adds energy. No, the photon doesn't add energy. The photon gets a little bit more energy, making it a shorter wavelength and showing up here on the shorter wavelength side of the spectrum. So at the same time that we have a process where we excite a vibrational state in a molecule, we can also have the process where a molecule that's already in a vibrational state transfers its vibrational energy to the photon in the scattering process. If you look at the peak heights, you see that these peaks with the longer wavelength are much higher than the peaks at the shorter wavelength, which shows you that the process of gaining energy is for the photon has a lower probability than actually losing energy to the molecule. And I'm going to give you a primer already. How can a molecule get already in an excited state? If I take a gas, how can I, let's say, already make the molecules vibrate?
Maybe by increasing temperature?
Yes, very good. If you increase the temperature, you increase the energy in the gas, we increase the amounts of collisions. And in these collision processes, you could excite a vibrational state. And so what you can say now of these already occurring vibrational states in the molecule, they're thermally excited. They're controlled by the temperature of the gas. And so it is not unreasonable to assume that when we increase the temperature of the gas, that also the number of molecules that are in a vibrational state will increase. And so that with the temperature increase, also the peaks here of these molecules will, of the peak of these emissions will increase. Okay. So let's go back to the evolution of Raman spectroscopy. Yeah? So from 1928 to 1960, not much happened. That is because powerful sources were not available to study this effect. But with the invention of the laser in the 1960s, Raman spectroscopy really took off, and especially in the 1980s with the availability of very sensitive detectors. And for instance, the charge-coupled devices, CCDs, that you're right now all familiar with. I mean, you have one in your phone. They're very efficient in capturing the light, and so that allowed the progress of this research field. And also the development of lasers in the near infrared. And then at the beginning, it was the study of these vibrational levels in molecules and how could you characterize them. But also it was realized that you could look at the Raman spectra of biomolecules, and that started the field of biomedical applications. As we will see later, these vibrational levels in a molecule are very specific and are very narrow. So if you look at these emission lines that we see here, they're very narrow. And that is a nice feature because it makes them very distinct from a background or a very broad fluorescence that is emitted. It allows you to characterize a molecule by what we call its fingerprint. It's very detailed graph of its vibrational levels. Okay, if you then look at molecules, how many different vibrational states can a molecule have? In how many ways can a molecule vibrate? And you have to look at basically at the number of atoms in the molecule. And then you can show that the number of vibrations that are present in a molecule is 3n minus 6, where n is the number of atoms in the molecule. And it's actually a little bit higher for linear molecules that perform a perfect chain. Therefore, the number of vibrational levels is 3n minus 5. That's here. So interesting then is that each molecule has its own very specific vibrational spectrum, which can be used now for identification of that particular molecule. So besides the molecule you're looking at, the spectrum also contains information on the local environment of the molecule. For instance, is the molecule in a crystal form, which in general reduces or changes its vibrational level? Is it in an acidic environment? What is the temperature? And so you could use Raman spectroscopy to measure the temperature of a gas. And there are two important techniques to record these vibrational spectra. One is direct infrared absorption, and the second one is Raman spectroscopy. And so I started this lecture with discussing Raman spectroscopy. It turns out that's an effect that is associated with vibrational levels in the molecule, but the Raman process is not the only way you can excite these vibrational levels in the molecule. We could also use a light source with a wavelength that matches directly to the vibrational level. And so then we would excite the vibrational level directly and not emit another photon. So that is the infrared absorption spectroscopy. And then the process I described is the Raman spectroscopy. So to summarize, if we only distort the electron cloud around the molecule with no energy transfer, it's elastic scattering or Rayleigh scattering. If we induce a nuclear motion, then there is energy transfer from or to the photon. We call it inelastic scattering, and then the vibrational levels of the molecule are involved. Vibrations that cause a change in the dipole of the molecule are infrared active, and vibrations that cause a change in the polarizability of the electron cloud around the molecule are Raman active. Now, these two are actually fairly complicated statements. These two, and I will go into detail in the next slide to explain to you what it means to have a change in the dipole or a change in the polarizability. But let's start with a change in the dipole. So a molecule can have a dipole moment if the charge is not equally distributed in the molecule. So it could mean that one side of the molecule is slightly positively charged and the other side of the molecule is slightly negatively charged. And that means there's an electric field across that molecule, or in other words, a dipole moment. So it is molecules that have a dipole moment that are infrared active, which means that they can directly absorb a photon. And then let's go to the polarizability. So the polarizability of a molecule is basically how tightly is the electron cloud around the molecule bound to the molecule itself. You can imagine if it's a very highly charged molecule, very positively charged nuclei, that they exert a lot of force on the molecule, on the electron cloud around it, especially if the two atoms are very close together. If they're very close together, you can expect the electron cloud around the two atoms to also be closely packed. But if you have a molecule where the two atoms are very far apart, then the electron cloud around it is dispersed over a much larger area. And the binding of these electrons, the forces they feel from the nuclei, because the distances are larger, is less. So you could say this is an electron cloud that is less strongly bound to the atom nuclei. So if we have an electron cloud that is not so tightly bound to the nuclei of the atoms, you can imagine that it's easier to make this electron cloud shake, or the amplitude of the motion of that electron cloud will be larger, and so it's easier, so to speak. Let's say the electrons are bound with the weak spring, and then it's easier to bring the spring into motion. While instead, if they're tightly bound, it's much harder to bring the spring into motion. So this effect of how easy is it to distort this electron cloud is called the polarizability of the molecule. And it's this polarizability that is responsible for the Raman activity of the molecule. So if you then look at the energy levels or the wavelengths that are involved in this in these vibrational levels, so in other words, what kind of wavelength of the light do I need to use to directly excite the vibrational level? That wavelength is in the order of 2.8 to 12 microns. So that's a much larger wavelength than the visible light. And so I'm going to give you examples now of this infrared activity and the Raman activity. And as an example, we will look at CO2. So it's a simple molecule. It's 3 nuclei, the carbon in the center, the oxygen at the edges. So when we look at this molecule, so here we have the CO2 in the center, the carbon at the edges, the oxygen, and let's see what kind of vibrational levels we can have. And I have to look closely now. If I look at this one, this vibration, it is the 2 oxygens on the outside that move away from the carbon and then move back in again. So that is the vibration of the, if you can see me on the screen, that is the vibration of the 2 oxygen atoms with respect to the carbon in the center, and the carbon doesn't move. So that is this vibration that I show here. And then the question is, does this molecule have a dipole moment? And the answer is no. So the charges are equally distributed around the atoms. So it doesn't have a dipole moment. And sorry, I have to be more precise. The dipole moment doesn't change during the vibration. So it's more or less the same. But if you look at the polarizability, we can see that in this case here, the oxygen atoms have moved in. Now it's a smaller molecule, it's more compact. So the electron cloud is more strongly bound to the atom cores. And if you then look at the location where the 2 oxygen atoms are far away from the carbon, the electron cloud is also spread out more and less tightly bound. So in this case, for this vibration, we have a change in the polarizability of the molecule, which we call here the alpha dq is not equal to 0. So let's take a look at another vibration. So now we look at this vibration here, and in this vibration, the 2 oxygen atoms stay more or less in place. But it's the central carbon that starts to move back and forth. So we have this carbon here. The carbon is in its equilibrium position. Here it has moved to the left, and here it has moved to the right. So it's the 2 oxygen atoms staying stationary, and it's the carbon in the center that oscillates between them. And if we then look at how is the charge distribution in the molecule for this vibration, we can see that the charge, the molecule is more positively charged on the left side when the carbon has also moved to the left, and the molecule is more positively charged on the right side when the molecule has moved to the right. So it's for this case. So here we have a change in the dipole moment of the molecule, and like I said before, change in the dipole moment is associated with an infrared active vibrational level of the molecule. If you look at the electron cloud around the molecule doesn't change size. So the electron cloud stays more or less in the same position for the 3 positions of the carbon during its vibration. So there's no change in the polarizability of the molecule. And if you look at the 3rd vibrational level, it's a bending vibration. So here the molecule is in its rest state, but now the carbon in the center is moving up and down like this. And so here to the left, the carbon is above the 2 oxygens, and here the carbon is below the 2 oxygens. So this is now what we call a bending vibration of the molecule. And again, if we now look at the charge distribution in the molecule, due to the motion of the carbon, we get the upper part of the molecule being more positively charged, and the lower in this position of the carbon, the bottom half of the molecule is more positively charged. So again, for this vibration, we get a change in the dipole moment, which makes it infrared active. And then if you look at the distribution around the electron cloud around the molecule, that stays more or less stationary during these 3 positions of the carbon. So if you then look at the spectrum that we can expect, we will see if you look at an absorption spectrum, so let's say we send in a very broadband lamp with a very long wavelength between the 2 and 12 micron wavelength, we see absorption peaks at this location and at this location, and these absorption peaks correspond to the absorption of a photon and then the excitation of a vibrational level in the molecule. For this peak, it's this vibration, and for this peak, it's this vibration here in the molecule. If we, on the other hand, send in a wavelength of a much shorter wavelength, we can induce the Raman scattering process. So now we excite the vibration in the molecule, and a photon of a longer wavelength is emitted. That's this photon here, and that is the Raman active vibrational level of the molecule. Okay. So that's important to realize that you are not able to excite an arbitrary vibration in a molecule through a Raman process, or you can excite an arbitrary vibration in a molecule with absorption. They're separated into absorption or infrared active and Raman active. Okay, so let's take a closer and actually a classical view of that scattering process. So we have an interaction between an electric field of the incident photon and the molecule. So we can describe the incident electrical field, EI, it's the incident field, as an amplitude E0 oscillating with a cosine that is given by 2 times pi times the frequency times time. So this EI describes the oscillation of the electromagnetic field as a function of time. And this incident field induces a molecular electrical dipole, a dipole in the molecule itself. The dipole in the molecule. With the dipole in the molecule, I mean that the electromagnetic wave distorts the electron cloud, puts it into motion, and then the charge in the whole molecule is not in equilibrium anymore, and we get a dipole moment. And that dipole moment P, that is given by a constant times the amplitude of the incident field. So the induced dipole in the molecule is proportional to what we call the molecular polarizability. alpha, or the ability to distort this electron cloud. And it tells you how easy it is to distort the electron cloud around the molecule. So the molecular polarizability changes with the bond length, or the distance between the two molecules. So we can say that how easy it is to distort the electron cloud, that parameter alpha, depends on the distance between the two atoms in the molecule. And so it's given by a constant times the difference in distance from equilibrium times the first derivative of that polarizability with the distance between the two atoms. So this is basically a Taylor expansion, the first two terms of a Taylor expansion of how the polarizability changes with the distance between the two atoms in the molecule. And we can write now that R minus R0, we can parameterize it with the parameter Q, which is basically now the how far the nuclei have moved out of their equilibrium position. And so with this, we can describe the polarization that is induced in the molecule, and we describe that with the parameter Q, and Q was the change in the equilibrium position of the molecule, and that is given by the amplitude of the vibration of the molecule, how much are the atoms move, times a cosine 2 pi frequency of the vibration of the molecule times time. So what we have now is that the polarizability is given by a constant plus the derivative of the polarizability with the change in the distance between the molecules times that Q0 times the vibrational frequency of the molecule. And so this part here, Q naught times cosine, is just this Q now written out as a function of time with the vibrational level of the molecule. And so what does this mean now for that dipole moment of the molecule, the field that the molecule generates itself? Well, let me see. So in this expression here for the electric dipole moment of the molecule, we write out now that alpha that we have written as a function of the bond length, and we write it as a function of the incident field. And so we get this P is equal to alpha E. And so we get P is alpha 0 times the incident field. This is the incident field times the incident field E is E naught cosine 2 pi V incident T. This term, this cosine multiplied with this cosine, and the product of two cosines you can write as a sum of the sum of the sum and the difference frequency. So that is done here. And so the product of these cosines are now written out as a sum of the sum and difference frequency. And so what we see is that the dipole moment of the molecule, or in other words, how the charge changes in the molecule, oscillates with the incident field. And actually this generates now the scattered field. This is our Rayleigh scattering term. We see here a term that for the dipole moment that oscillates at a lower frequency, sorry, at a higher frequency than the incident field, because this is the sum of the two frequencies. That is what we call now the anti-Stokes scattering. And we see a term that oscillates with a lower frequency, and this is the Stokes term. And so with this derivation, we have basically shown that if the that with the electromagnetic field that is incident on the molecule, we introduce a dipole moment, and that is because the molecule is polarizable. And because it's polarizable and the polarizability depends on the bond length, we can link now the dipole moment of the molecule to the internal vibrations of the molecule. And we can show that the dipole moment oscillates at 3 different frequencies: the Rayleigh frequency, elastic scattering, anti-Stokes frequency, and the Stokes frequency. Okay. So these molecular bonds all vibrate with their own specific frequency, and this frequency actually depends on the bond strength, or you can call it the spring constant between 2 atoms, and the masses of these 2 atoms. And you can derive, this is basically from classical mechanics, that the frequency with which these 2 molecules, these 2 atoms will oscillate with respect to one another is given by the square root of the spring constant between them, the sum of the 2 masses divided by the product of the 2 masses of the molecule. So this now basically is a very basic derivation of what to expect for the oscillation, the frequency of the vibration. So that scattering process that I just described, we like to describe in what is called a Jablonski diagram. And it's named after Polish physicist Alexander Jablonski. And it's a way to depict the energy levels in the molecule and what the energy of the incident photon is with respect to the internal energy levels of the molecule. And so what is shown here is the electrons are in the lower electronic band around the molecule, but we can excite vibrations. And so these energy differences, so remember, this is an energy axis. This difference in energy is the vibrational energy of the molecule, and you can have different vibrations of the molecule, so you have different excited states of the molecule. You can excite the molecule from its ground state into this vibrational level, or you can excite it into this vibrational level, or you can excite it into this vibrational level. The other thing we have to remember, of course, is that electrons can also be excited to higher bands in the atom. So we can create an excited state of the molecule. And this is now a band for an excited state. And within that excited state, again, we can have changes in the energy of the molecule due to the vibrations in the molecule. So you could say, hey, you excite an electron to a higher orbit that increases the energy of the molecule. If you add now a vibration to it, you add another bit of energy to the molecule. And so these levels now that you can see here are the energy levels of the molecule as a whole. The combination of the vibrational energy and the electronic excited states. Now these diagrams are relevant because now we can also plot the energy of the incident photon into this diagram and show, how it is related to the energy of the molecule itself. And so the Raman process, I have described it so far, is we have a photon that has an energy somewhere here, and then there's a photon emitted of a shorter wavelength, of a longer wavelength, lower energy, down to this level, and then we excite the molecule from its ground state here to its first vibrational level. Now, why is this relevant? Because later on we will see we can also use a photon that has this amount of energy. And you can immediately imagine that different things will happen here, because now you can directly excite an electronic state of the molecule. So what will happen then? Leave that for later. So basically we have a molecule that has a ground state and its excited states here into the different orbits of the electrons around the atom. And these ground states split up into different vibrational levels. Like I said, the energy that is along this axis is the total energy of the molecule, sum of excited states and vibrational levels. So this depicts the orbits of the electrons around the molecule, and this depicts the motion of the molecule, the atoms in the molecule, and the vibrational levels. So what are now the energy of these vibrational modes? And like I showed you before with the derivation from classical mechanics, the lighter atoms lead to higher oscillation frequencies that are higher. So we get more energetic vibrations. And if we have heavier atoms, we get slower vibrations. So the energy shift that is involved starts to depend on the masses of the atoms in the molecule, and that is why it allows you to really identify individual molecules. So here we see two different vibrational levels where this is the higher energy vibration, so associated with the light atoms, and this is a lower frequency vibration associated with the heavier atoms. And so if we now take a look at let's say a complicated molecule like cholesterol, and the molecule structure is shown here. It consists of many individual atoms. And you can imagine now that if you want to look at the Raman spectrum, there are very many different vibrational modes present in this molecule. And so for instance, we have a peak here that is called the C double bound C stretch mode. That is where the two carbon atoms are moving in and out with respect to another. Here we have the CH2 and CH3 bend mode. So here we have a CH3 molecule. Here we have a it's the CH2, and this is, I think, the CH3. And that whole complex can now kind of wave at the end of the whole molecule back and forth like a bending motion. So this is then a bending vibration. And here we have two more bending vibrations, and we have here two C single bound C stretch modes. And well, overall, you can see that there are many peaks present in this spectrum, and this is what we call that fingerprint, because this is a cholesterol molecule. The Raman spectrum is very specific, very many narrow peaks, and so when you record the spectrum, the Raman spectrum of light that is being scattered off this molecule, you can identify it. And you can imagine that if there's even a mixture of molecules, that each molecule has its own really specific spectrum, and that you can deconvolve them to determine what the concentration is of one molecule versus another. So this is what makes it such a powerful technique. Okay, so there are some symbols that are missing in this. Okay, I think that is the energy of a photon is equal to h times c divided by lambda, and this is also lambda, and this is also lambda. So we have the energy of the incident photon that is given here, and that must be then in it. And then if we look at the energy of the vibration, that must be the energy of the incident photon, that is shown here, minus the energy of the emitted photon. So we can describe this vibration now as an energy difference that is defined by the incident energy of the photon and the emitted photon energy. And as you can see, this vibrational energy depends on the wavelength is 1 over the wavelength, or 1 over a distance. So the Raman shifts are in general depicted as a unit 1 over length, and they've actually chosen the unit 1 over centimeter. So that is the common way to report the energy shifts in a Raman spectrum. And I just want to get you a little bit familiar with these energies. So if we take, for instance, the near infrared excitation at a wavelength of 830 nanometer, that corresponds to 12,048 inverse centimeters. So now the question is, what if we have a typical Raman shift of 1,000 inverse centimeters? So that 1,000 inverse centimeters is now an energy level of the molecule, vibration level. What is the wavelength of the emitted photon? So the incident photon is 830 nanometers, and the emitted photon, well, that's the question, and that is for you to calculate. I'm going to find some scrap paper to do the calculation myself too. So let's help you out here. Huh? So we have, let's first verify how we get to the 12,048 inverse centimeters. So if you do 1 over lambda is 1 divided by 830 times 10 to the power minus 9 is equal to 12,04819 meter to the power minus 1. But we want to express it into inverse centimeters, 1 over centimeter. So there's a difference of a factor of 100. And so this is equal to 12,048.19 centimeter to the power minus 1. So that is how we can convert our incident wavelength to inverse centimeters. And then the typical Raman shift was 1,000 inverse centimeter. So what does that mean for the energy of the wavelength? The energy of the photon that's being emitted. A 1,000 inverse centimeter of the energy is absorbed by the molecule. And so that leaves us with 11,048 inverse centimeter as energy for the for the molecule. Sorry, for the emitted photon. And so we know that that is 11.04800 meter to the power minus 1 is equal to 1 over lambda r. And that gives us then for lambda r Anybody has an answer? Anybody with a calculator can type this in? Not the hardest question. Is somebody speaking up? Oh, so Yep, saw me about.
It's 905 nanometers.
Yes, very good. I got the one answer here. 905.125 nanometers is the emitted wavelength of the photon. And just to give you another idea of how sharp are these Raman line widths, so these line widths are on the order of 10 inverse centimeters. And remember, this is an energy scale, so that means that they're fairly narrow vibrational levels. So 10 inverse centimeter. What kind of shift does that mean in terms of the emitted photon? So the idea is the vibrational level has a width of 10 inverse centimeters. We know that the scattered photon has a wavelength of 905.125 nanometers, but the spectrum that is emitted will have a certain width. And so what is now that width in wavelength? And so what we measure is intensity as a function of wavelength. And then we measure a peak, but that peak has a certain width. And that certain width is determined by the width of the vibrational level. And this width is then 10 centimeter to the power minus 1. And what does that mean for this width in terms of wavelength? And so if I would like to know what is the full width half max of this peak in expressed as delta R, what is it? And what I'm going to do is I'm going to leave this for you as an exercise. And I will post the answer next time. But please make this exercise, you familiarize yourself with how to calculate with energy shifts and Raman spectrum. And also you get a little bit of a feeling of how much is a shift, what does it mean? Okay, we are entitled to already a break, or actually 10 minutes ago. So if you want to, cool off, grab some water or make some tea, this is your chance. And I would like to resume in like 15 minutes. 20 minutes before 5, if that's okay. Wouldn't delta lambda R be quite broad? I'm not sure who asked the question. Can you expand a little bit on why it would be broad?
Right, so for the typical Raman shift, we had about 1,000 inverse centimeters. And doesn't that correspond